recording on this. Okay, so share screen. Okay, here's my entire screen. So notice here, so I've downloaded the zip file with all these Java files on it for module 4 for Rabbit Hunt. What you're going to need to do is you're going to need to take them and you're going to need to put them all in the same folder. If you're working in IDE like I am, or like Eclipse or IntelliJ, you drag them all into the SRC folder. Okay. There's a bunch of, this is your code, all the code for the project. It looks like a lot of code and it is, but guess what? You only care about one file in terms of coding, which is the Rabbit class. That's it. And in fact, we only care about one method, which is filling out this method, the decide move method. That's it. That's your entire job, filling out this one method. Everything else is just part of making sure that the program actually does stuff. In fact, it is a fully working program at the moment. We can run Rabbit Hunt to see what it does. Okay. And I got this window over here. It will show up white, or maybe nothing will show up at all. It depends, because it will depend on your system, how this appears at first, because of just the way that old, very, very old Java code works in modern settings. But this is the way it looks. All right. The red is the fox and the brown is the rabbit. And the game and it's basically a game. These guys, the rabbit, so I'm just hitting it step by step now. The fox and rabbit take turns moving. First the rabbit moves, then the fox moves. I think it might actually be random who they go first. It doesn't matter, but they take turns one at a time. Okay. The foxes will attempt to eat the rabbit by landing in the same space as the rabbit. The rabbit, as it stands right now, just moves randomly around. The game ends when the fox eats the rabbit, or if the rabbit somehow survives 100 turns, the rabbit will win. Make sense? So foxes, and they move at the same speed, one square at a time, right? And it's one of those weird diagonal grids where going diagonal, it's Euclidean distance. So going diagonal takes as much time as going any of the cardinal directions. All right. So what we have here is, so this is a GUI essentially. Now this was made almost over 20 years ago, and it follows a very classical model for GUI that is still used today, which is called model, view, and control. A model is the internal logic that the program uses. The view is what we see here. Okay, so when I hit the Rabbit Hunt class and run it, the stuff we're seeing as users is the view. Okay. The control is all this stuff at the bottom over here, which allows me to mess with the program. You don't really need to understand all of that. That's just kind of what it is there. So, how does this work since it's a running program already? Your goal is to make the rabbit survive as much as possible. Your grade is as follows. You run the grader. And then you will get a grade based off of how often your rabbit survives out of 300 attempts. If you feel like you need to, you can bump it up to 3,000 attempts, but otherwise the only class you can modify is Rabbit Hunt. Make sense? Is Rabbit, not Rabbit Hunt. This is the only class you can modify, the Rabbit class. You can't touch the other classes. Make sense? Like, because if you turn in your code, all I want you to, all I need you to really turn in is the Rabbit class, because that's where all your code is going to be anyway. So, and here's our rabbit. This is the constructor. You don't need to worry about it because you're not going to be changing it, most likely. Here instead is the decide move, which basically that's what gets called when it's time for an animal to decide what move it is. A rabbit is an animal, so it can use all of the methods that are in animal over here, and that's got a bunch of them, such as figuring out distance, figuring out look. We'll take a look at what those do in a second. Okay. Right now, all it does is return random.model.min direction, model.max direction. These are a few just static variables that are constants. They're just stored in, they're stored in our, they're just stored, okay, inside of the code so that, in model so that we don't have to remember what the heck are min direction and max direction, 0 and 8 respectively. Okay. Specifically, if we look at model, all of the directions are numbers. Wait. Oh, right. Those are not actually errors. Those are just documentation things. Okay. North, we encode north as 0, northeast is 1, east is 2, southeast is as 3, and south is 4. Make sense? It just goes up clockwise. Okay. And 8, it represents not moving anywhere. Okay. When an animal when we tell an animal to decide on its move, it will return an int, right? Here that we've got int decide move, and it says, I'm going to return a number. That number is going to be the direction that it wants to move in. If it's an invalid direction, like if it's a direction that it can't move in, then it will just, then it just won't do anything. For instance, here I'm going to return 0. Now the rabbit on its move will always move north. Make sense? That's not a good strategy, but it's something. Okay. So here run. And notice, okay, yeah, he's not moving. But that's because he's got a bush right there. Bushes block line of sight and line of movement. See, and he stops moving. You know, he's returning an invalid number. Okay. So, all right. So let's get a better view of what, and if you really want to, dive down into it, you'll start out by running this a lot and to kind of debug what's going on. And then eventually you'll just be running the grader. When I hit step, which makes them move one at a time, you'll see that there's this basically yellow laser that shoots out from the fox. That's it calling the look function, which is the key to survival for the rabbit and the key to hunting for the fox. Okay, so here's a bunch of code from fox. Here's what you don't want to do. You don't want to take the decide move from fox and just drop it into rabbit. If you do that, you're going to have a bad time. Not because these errors, these are super easy to kind of just, but because this is the code for a predator. A predator has to work hard to find its prey. Make sense? Okay, has to work really hard to find its prey. Let me just stop sharing for a second. What I can do is I can now just share the app so that way it shows up better on your screen. Okay. So the fox is going to be working really hard to find the rabbit. But the rabbit, honestly, his job is fairly straightforward. Don't get eaten. And he certainly doesn't want to find the fox, because if I can see the fox, that means on my turn, the fox can see me. So in general, there are two strategies for survival. I recommend the second strategy. The first strategy is called kiting, which if you've played MMORPGs, you know what that is. For those of you who don't, typically that refers to the fact that basically there might be a big monster that you want to, instead of just fighting it, you wear it down over time by basically poisoning it or something. And then one poor player, he decides he's going to kite that monster by running away from it and just doing his best not to get eaten. Okay. It's a valid strategy. It is a time-consuming strategy, and your fun may vary depending on your personality. Okay. That is hard to program. Instead, what you should do is exploit line of sight in this program. What do I mean by that? What I mean by that is that the fox can only see in straight lines. Okay. So let's look at the code before I go back to that. So the way the fox goes is that his code over here looks around for the rabbit. This is the only, this for loop over here and this if statement over here is the only thing useful from the fox code, if that makes sense. Okay, that is the only thing useful where you say, okay, I'm gonna for I is int I is equal to 0 because min direction 0, I is less than or equal to max direction. So I go through all the compass directions. And if look I is model.rabbit. So look is a function, it's from animal, and it says, hey, given a direction, tell me what's there. And it will say it's a rabbit, it's a wall, it's a bush, it's a fox. One of those four things in that direction. It's going to tell you the first thing basically in your line of sight. Okay. And then for the fox, his job is, oh, if I see the rabbit, great. I'm going to get close. I'm going to track that I can see the rabbit now, and I have seen the rabbit, and I'm going to try to get closer to it. I'm going to store that direction and get closer to it. The rabbit, as I'll explain in a bit, doesn't need to do any of that. It's worth re-mentioning that multiple times. Okay. Next, what I do is that if I've seen the rabbit this time or recently enough that I'm keeping track of him, then as long as I haven't landed on the space that I think he should be on, I'm going to keep track of that. And I'm going to say, I want to move closer to the rabbit. Right? Otherwise, if I get to the space that he's at, something has gone wrong. I've lost him. The rabbit was slipped away from me. And so I'm going to choose a random direction to go in. Then otherwise I say, okay, if I haven't seen the rabbit or I lost track of it, then I'm going to continue going in the direction that I was going on. And this is the other bit that's going to be useful for you. This can move model.turn current direction and then some number. What this says is that, okay, I've got this direction and I'm going to move in that current direction. Okay, I'm going to move towards that current direction, but to the right, or towards that current direction and to the left. I'll explain turn in a bit. But basically it says if there's an obstacle, I try to just like sidestep it a bit, right? Consider current direction forward, right? I'm going to try to go, if current direction is north, I'm going to try, and I can't go north, I'm going to try to go northeast and northwest. Okay. Otherwise, I'm going to choose a random direction. Okay. When we look at what the fox does, sorry, what the rabbit, so yeah, what the fox does. Okay. When we look at what this guy does, run, you'll see that he moves in a current direction until he sees the rabbit. And if he doesn't see the rabbit, he just kind of paces back and forth. Okay. And once he gets to a spot where he can't keep going back and forth, he'll basically bounce off that surface and go and track him down. So see, there you go. And he updates every time he sees the rabbit. Every time I see the rabbit again. Okay. So the key to this is the rabbit survival is this over here. That look function. Why? Well, watch it in. You see that missed the rabbit, even though it was just one column row away, but it missed it. Why? Well, because again, you can only see in straight lines. So if I reset this, right, run, set this, come on, get to a more central location, Fox. There we go. Step. Okay. So here's the thing. This is actually fantastic for my explanation. So the fox just moved into this space. The fox's line of sight, give me 1 second. The fox's line of sight is by these lines. Okay. And my diagonals are drawn very badly. Okay. So, okay. So just ignore the fact that I'm terrible at drawing diagonals. Okay. So by all accounts, the rabbit Okay, it's now the rabbit's turn, and by all accounts, this should be really bad for the rabbit. But the rabbit does have a way out because because it's a turn-based game. That means that the fox has moved from here to here, right? The fox has moved over here. Okay, which means that his turn is over. That means he can't see the rabbit. He won't be able to look again until it's his turn, which means it's the rabbit's turn. And if the rabbit, well, he can just move because this is a giant blind spot. This is also a giant blind spot. Make sense? So the rabbit strategy is very, very, very simple. Okay. If on my turn, I see the fox, move out of the fox's line of sight. Otherwise, if I don't see the fox, stay put. That's it. Okay, so what does that mean to move out of the fox's line of sight? Let's pretend for a second that we're not here because this will make second. Okay. So suppose the rabbit is over here. What directions are most advantageous? Let's go ahead and look at what directions are most advantageous. Is going in this direction good? No, that's a terrible choice. Okay. That's a terrible choice. Okay, because you're going towards the fox. Similarly, going directly away from the fox is actually a bad idea because you're still in the line of sight. Okay. This is a dangerous move. And so is this a dangerous move? Assuming the bush wasn't there, right? But they're better than nothing. I would not necessarily worry about those. Okay. So honestly, now that we know that like going directly back isn't a good move, what I would say probably going here or here would be good moves, would be the really good moves. And going here or here would be our backups. Make sense? Okay, so how do I calculate that? That's where the model.turn function comes in. Okay. Model.turn says, given a direction, give me a number of 45 degree turns from this. What do I mean by that? So if I told, so let's go ahead and see actually, I'll show you in action here. Okay. So stop sharing. Share. Okay. So let's go ahead and take a look at the fox, and I'll get you to where my students typically are when they take this class and they get, okay. So first off, let's look at how we look around for the fox. Okay. This is the only bit that's useful. Okay. That's this bit. That's how we look around for the rabbit. So we can use that in the rabbit to look around for the fox. It's the only bit I ever want you to, don't copy anything from else from the fox code because that would be terrible. In fact, I'm not going to copy it. I'm going to do it myself. So by default, what I'm going to want to do is I'm going to want to stay put. In fact, actually, that gives me a marginally better grade than moving randomly, if I recall correctly. Yes, I survived 27 times out of 3,000. So yes, marginally better. Okay. Now, what do I want to do? Okay. So rabbit, let's go back here. What we do for rabbit is we say, okay, how do I look in every direction? I say for I is less than model dot min direction. Okay. And it's less than, so this is a very common error here. So pay attention if you're watching this recording. Okay. Very common error. You want to do less than or equal to here for model dot max direction, right? Because you want to go through all the directions inclusive. And that's exactly what we're doing over here, right? Less than or equal to. So look for each of those directions. I'm going to look in that direction. Okay. For each direction, I'm going to look in that direction. And if it's equal to a fox, then I'm going to do something. Okay. So, okay. Now what should I do? Well, what I would like to do, let's just practice and not think about this for a second. I'm going to do a move that I said was not that great. I'm going to move directly away from the fox. Now, how do I do that? Okay. What I'm going to do is I'm going to say, I'm going to return. I'm going to actually help you with this. If I can move, so if can move, model.turn. Okay, so first off, can move says if I can move in this direction, because if there's a wall there or a bush there, I obviously can't move there. So if I can move in a direction, model.turn. Okay. And again, I normally wouldn't give out so much of this so quickly, but summer. Okay. So if model.turn in that direction, and I give you a number, it's 4. So model.turn says, given a direction, I, okay, I'm going to make 4 45-degree turns clockwise. That's what it does. Given a direction and a number of times to make a 1/8 turn clockwise, return the resultant direction. That's not AI generated, by the way, or anything fancy like that. That's just literally reading the comment from model, from model.turn. Right? That's just IntelliJ being smart and picking up the documentation for me. Okay. So what does that mean? A number of terms? Well, this says I'd like to make 4 45-degree turns. So if you look at me personally right over here, the guy speaking to you in the Zoom window, if that direction towards you is direction I, then making 4 45-degree turns would be 1, 2, 3, 4. So directly away from you. So this says if I can move directly away from the fox, if I can move in what direction? The direction that's directly away from the fox, return that direction. Make sense? Okay, now I survived it just a little bit. Notice that 1% survival rate gets you a 10% grade. That's not the way that your grade is calculated is the square root of your survival rate times 10. The square root of your survival rate times 10. So in other words, if your guy survives 81% of the time, the square root of 81 is 9 times 10 would be equal to a 90, right? So you just need an 81 to get an A on this one. Okay. It also means that diminishing returns basically are a thing because your grade basically goes up really quickly and then it just teeters off. So like a 64% survival rate gets you an 80. And a 1% survival rate, as a result, 1 times the square root of 1 is 1 times 10. That's why we get 10. Okay. So now, again, we can see this, and if you want to run this yourself, you can see this. Now, here's the thing we want to check out. We said that, what about moving directly? Instead of moving that, why don't we try moving back and to the right? Okay. Back and to the right. Okay. Make sense to everybody? You'll find, so moving back into the right, just simply, if I see him move back into the right, I survive there. So here's the way the program should work. Okay. You can basically, you just need a bunch of if statements here saying, hey, what direction should I move in? If I see the fox, I'm going to try to move in one direction. If I can, great. If I can't, then I try another direction. So you'll want a lot of if statements, like another if statement here and so on and so forth. The key here is that the order you check the directions, even the symmetrical directions, matter because the fox has a bias in the way he turns. So going right versus left, or left versus right, or back into the left versus back into the right, that makes a huge difference. Make sense? And I'll even be nice and I'll show you what I mean. That doubled the survival rate by going back into the left versus back into the right. So you want to try your hand at that. Okay. This is actually a ridiculously easy program now that I've explained this part. Okay. Like if you think it's still hard, then you're overthinking it because you're literally, because I basically said, and the rest of your job is to write the if statements. But this is literally what I give the undergrads for the first week. I just give them a day to work over it by themselves. And unfortunately, in the grad class, in grad school, I would have done that the same way, but or normal grad semester. But in summer, more's your luck, we don't have that time. So you get the accelerated version of this. It's actually a very easy program. Or rather, I should say, it's very easy to get around to get somewhere in the 85% survival rate by just making if else statements. Getting above a 90% survival rate, a 92% survival rate is a bit masochistic. Okay. So, the only way to actually get a 100% survival rate is to cheat. And in the sense the only winning move is not to play. And I'll leave you to figure that one out if you really want to. But but otherwise, going through this and fixing those if statements would do it. Okay.
Hmm.
So I'm going to go ahead and stop recording.